All right, welcome back. Today we're putting on our detective hats because we're going to crack a really fascinating case. How do machines actually make sense of our world? We're going to go from a simple flower to a complex opinion and uncover all the clues.
I mean, really think about that for a second. It's a real head-scratcher, isn't it? How can a chunk of code, a machine that only thinks in zeros and ones, possibly get the subtle differences between flower species, or figure out if you loved or hated that new coffee you tried? Well, that's the exact mystery we're going to solve today.
You know, every good detective starts with the evidence. And in our world, the evidence comes in two main forms. On one hand, you've got structured data. Think of it as neat, organized numbers in a spreadsheet, like the classic iris flower dataset. And on the other hand, you've got the messy stuff, unstructured data. We're talking free-flowing text, like thousands and thousands of Amazon fine food reviews. Two totally different kinds of clues.
Okay, so before we can interrogate our evidence, we have to get one thing straight. We need to understand our main tool, the computer. And to do that, we have to learn its native language. This right here is the absolute key to everything. A computer doesn't see petals, it doesn't smell coffee, it doesn't read a word like delicious and feel happy. Everything, and I mean absolutely everything, has to be translated into the only language it gets, the language of numbers.
And the most important word in that language is something called a vector. It sounds fancy, I know, but it's really just a list of numbers, an array. But this one simple idea is how a machine represents the whole world, from the width of a flower petal to how you felt about your last meal. It is the universal translator.
All right, you ready? Let's tackle our first case. We're going to start in the nice, clean, straightforward world of structured data. We are officially on the case of the iris flower. So here it is. This is our case file, the iris dataset. We've got these really precise measurements for 150 different flowers, all laid out perfectly. Now, on the surface, the clues look pretty simple, but the real patterns, the good stuff, that's all hidden deep inside these numbers.
But hold on a second. Just staring at 150 rows of numbers, that's not going to get us anywhere. The clues are in there, somewhere, but they're hidden. So how do we even begin to find the pattern that lets a machine say, aha, that one is an iris setosa, but this is an iris virginica?
Well, a good detective always visualizes the crime scene, right? So let's plot the evidence. We'll take two of our clues, sepal length and sepal width, and just throw them on a scatter plot. And what do we get? A big, confusing blob of dots. There's no clear pattern here, no obvious groups. This is looking like a dead end.
But wait, what happens if we add that one crucial piece of info we already have? The species. Let's just color code each dot based on its species. And bam! Would you look at that? The blue dots, the iris setosa, they all clump together, way over here, totally separate from the others. A simple little visualization just cracked the case wide open. This is our first big break. And to take it even one step further, data detectives have this amazing tool called a pair plot. It lets us check the relationships between all our clues at the exact same time. And when we do that, it practically screams at us what the most important features are. Check out the plot for petal length versus petal width. The separation is almost perfect. These two measurements, that's the smoking gun. Case number 1 solved. Okay, that was the warm-up. Now for the hard part. Let's move on to case number 2. We are leaving the clean, orderly world of numbers, and we are jumping headfirst into the messy, chaotic world of human language. This is where the real detective work begins. So our new evidence file has over 360,000 Amazon food reviews. Just take a look at this one. As a person, you and I can read this and instantly we know it's a positive review. But how in the world does a computer, which only gets numbers, figure that out? It can't read words like great price or very fast. So, first things first, we have to clean up the crime scene. Before we can even think about analyzing the text, there's a ton of prep work. We use the star ratings to label a review as positive or negative. We get rid of any duplicates. And then we have to literally scrub the text, get rid of weird HTML tags, toss out the punctuation, just generally tidy everything up. So once the scene is clean, we finally face the main challenge of this whole case, turning these messy words into clean numbers. This whole process is called vectorization. And trust me, it's both an art and a science. So this is it, the central question. How do you possibly take a simple phrase like great taffy and turn it into a meaningful list of numbers, a vector, that a machine can actually do something with? The first technique we can use is the simplest. It's called bag of words. Imagine you have a giant dictionary with every single unique word from all the reviews. Then, for each review, you just make a vector by counting how many times each word from that dictionary shows up. It's simple, it's fast, but it's also kind of dumb. It treats the word great and the word taffy as two totally separate, unrelated things.
So we can get a bit smarter with a method called TF-IDF. Now, this technique doesn't just count how often a word shows up in one review, it also looks at how common that word is across all the reviews. It gives more importance, or weight, to words that are rare and meaningful, like taffy, and way less weight to super common words like the, or is.
But the real honest-to-goodness breakthrough is a technique that came out of Google called Word2Vec. This was a total game changer because it goes way beyond just counting. It actually learns the context and the semantic meaning of words just by looking at the words that usually surround them. It figures out that delicious and tasty are similar words without anyone ever telling it.
And this is where it gets absolutely mind-blowing. Because it understands context, it can learn analogies. It learns that the relationship between man and king is a lot like the relationship between woman and, well, queen. You can do simple math with these word vectors. Literally, you take the vector for king, subtract the vector for man, add the vector for woman, and the number you get back is incredibly close to the vector for queen. It's amazing.
Phew. So, after digging through both of our cases, what have we actually learned? It's time to file our final report and see what the big takeaways really are.
So, what's the real key finding from our whole investigation? The actual work of a data detective isn't just about building some fancy AI model at the end. It's all about the prep work, using visualizations to find the first clues, carefully cleaning up the evidence, and finding the smartest way to translate our messy world into the structured vectors that machines need. This whole process, this exploratory data analysis, that's where the case is truly cracked.
And that leaves us with one final question. Now that you've seen the real detective work that goes into preparing data, turning flowers and food reviews into numbers a machine can understand, what other big, supposedly unsolvable problems out there do you think data could help us investigate? What's the next big case for the data detective?